Okay, now it's time to define post-processing templates. Okay, okay, yeah, there we go. Post-processing, what is that? Well, basically, CST give us the option, the way, or the tool basically to define the results that we want to see from the simulation. For example, we want to see the gain and to see the beam width of our horn antenna at the elevation and at the azimuth plane. So for that we have here this button. Okay, this button we already defined it, but I will delete it to show the whole process. Okay, delete it and delete it. In order to, we are going to define firstly the gain. Okay, so far field antenna properties, and here we got the far field result. So before doing that, we got to make sure that we already define the far field that we want to simulate. Okay, I recommend you to have enough points to have the resolution that you want. Okay. Okay, so far field results, and here I always select all setting in order to have the whole control. All setting. You could leave automatic option in order to select the first far field, or you can also browse your monitor and select the first one. And due to we are going to proceed as a broadband option, you can select what CST is going to do is to analyze the first far field and then proceed the same way with the other far fields. And this, the reason is because we are proceeding in the broadband option. If we want to select just one frequency, we have to go this button. Okay, so for this particular case, broadband is the one. And let's select Cartesian in order to see the result properly. So regarding evaluation range, here we go. Here we go. A step size, I recommend to use 1. Okay, 1 degree. And we're going to define the gain in the azimuth plane or in the horizontal plane. Okay, just 1 second. Okay, I will put this window over here in order to see the whole antenna over here. Okay, now you see it clearly. Okay, broadband, pole Cartesian, step size 1. Okay, so azimuth plane, horizontal plane is going to be the for theta, the blue plane. The blue plane is the horizontal. So for that we got to define theta equals to 90 as we got here. Max value is the way to obtain the gain, and float mode we are going to go for realized gain. Okay, because realized gain has into account losses and different matching, so this is the realistic way to get the gain. Okay, if you want to see the directivity, you could select it, but for our case, gain is better because I want to see the efficiency, I want to see all these kind of parameters. Okay, so gain, and then we got axis. For this particular case, we got to say that we are simulating a vertical. Okay, remember that the polarization of this horn is like this, so we got a vertical linear polarization. Okay, so what do we mean by that? Well, basically, due to we got a linear polarization, we got a clear copolar component and a very low hopefully a very low cross-polar polarization. So regarding the copolar could be or theta or phi component, just one of these two. Okay, so in other words, for a linear polarization, it doesn't mind if we select absolute polarization, or if we select the the, the theta or the phi polarization, depending of the polarization of your horn antenna. So to make it easier, we are going to select the absolute. Okay, yeah, I think this is almost all, and we are going to rename it. This is gain in azimuth. Okay. Okay, so we could duplicate it in order to have the gain in the elevation plane. Elevation, change settings, and for that, remember, the elevation is determined by this red circle plane. Okay, so for that we got to change this range theta 0, then click constant phi, and the elevation plane will be for phi equals to 90. Okay, this remains the same configuration. Okay, now we got the gain in both planes. Okay, so now another parameter, important parameter, is the beamwidth. Okay, the beamwidth of the horn antenna in both planes. So for that, we are going to select the same far field results. There we go, settings. Here we select the far field. Okay, broadband, in order to see how the beamwidth behave, or how the beamwidth is affected by the frequency. Okay, Cartesian, step size 1. It's almost the same as we explained before, and here we go. There we go. We got here to select angular width. Okay, release gain. We select absolute, and here we could select the beamwidth, the minus whatever dBs beamwidth. Okay, we're going to go for this criteria in order to see the minus 3 dBs beamwidth. Okay, so 3, and this is for the azimuth. Okay, I will rename it like this, minus 3 dB azimuth. Okay, duplicate. Okay, and elevation, we have to change the planes as we did before. Now 0, and elevation. Okay, save, and there we go. We got gain and beamwidth. Okay, so now we are able to run a simulation solver. Okay, so simulation, we already defined all we need. Okay, so solvers is a good topic to talk about. For this kind of antennas, CST has a really good solver, and it is called like transient solver setup. For example, home window transient time domain solver. Okay, here if we select T solver, here basically it shows the mesh configuration that we are using, and which is hexadecimal. The accuracy is basically, the accuracy. If we select a higher one, it would cost, it would have a higher computational cost than if we select a lower value. Okay, so I usually prefer to select to go for this for 30. Okay, then ports, we are going to select our port, and yeah, I think it is almost what we need. Apply, and then start. Okay, so now the solver is running, as you can see here. Calculations, computing. We will leave it until the solver is done. Okay.